I guess, as review, we're looking at, this is 14.6 on directional derivatives and the gradient. And problem 35 was suggested because it has lots of parts and kind of tests a lot of the ideas, I think, of the section. So let's see what we do with this. Matthew, this was yours, you asked? No?
No.
Who asked this one? Alex? Okay. So when we do this, let's see, we have f of xy is the function square root of 2 plus x squared plus y squared. And they say, let's think about what happens. The point that we're going to be talking about, point P, is going to be the square root of 3 comma 1. Okay? So it says, find the gradient and evaluate it at P. And I guess I'd like to sketch a little graph. So let me just, since this is in the first quadrant, let me just do what I did on the last example where I just, had the x, y, z going on here. And so, if this is 1 and this is 2 and this is 1 and this is 2, let's see. I notice what's the highest that this one can possibly get? This function. Well, the square root of 2, right? So a little bigger than 1, right? And so I could say that the maximum value of this function is at 0, 0, square root of 2. Okay. If I plug in the square root of 3 for x, when you square that, that becomes a 3. So you might get up to the square root of 5. Oh, so this is the minimum value, right? This is a minimum value. Because if you throw in anything for x, you're going to be, it becomes higher, yeah. So it kind of swings up. And then in the y direction, if we go up to 1, it'll swing up, but not quite as high, right? So, okay, so I guess it's hard to visualize, but I have some kind of I guess I'm starting to picture that I have some kind of almost a cone, right? Where as x and y increase, you kind of move up this cup. That's what I'm picturing. And so I'm picturing the bottom point of that cup is that 0, 0, square root of 2. That make sense to you guys? Okay. So now the question is, what about that point, square root of 3 comma 1? I'll put that in green. That lives on the xy plane, right? That's in my two-dimensional space. And so y is 1, that's this line here. X is square root of 3, so it's a little more than 1, 1.7 or something like that. There's the point P. Now the point P, if I go straight up, I am going to hit the surface somewhere, and let me mark that up here. There's the point P. This is like, what should I call it? I'll call it P hat. P hat is the point on the surface, which the coordinates of P hat are square root of 3, comma, 1, comma, I guess I could work out what it is, right? Plug it in, 3 plus 1 is 4 plus 2. Wouldn't it be square root of 6? Right? So that's my P hat. Okay. So now we're ready. We want to compute a few things. So part A asks, let's compute the gradient and evaluate it at P. So remember, A, the gradient of f is given by, well, fx comma fy. And so, it's interesting, when I'm putting your test together, it'll be about the same, about a 6-page test. But I don't think I'm going to do 1 page per section. I don't need to. Maybe I will. I don't know. But I guess the point is that just by having you compute the gradient, I'll find out. I don't need gobs and gobs of partial derivatives, right? Because you're going to have to do it all test. Yeah. Well, here's the thing, right? I think the smart thing to do, if I want to make this test correctly, is if I want to give you challenging partial derivatives, do that on page 1. But if I want to test the gradient, don't make the partial derivatives too hard, right? Because if you screw that up, then I have to grade it. You understand? So I'll try to give you easier ones to do. Now, by the way, is this one challenging or easy? fx, for instance.
Not too bad.
1/2, and then it's stuff to the negative 1/2 times 2x, right? Yes? Of course, the stuff is 2. Of course, when you put something to the negative 1/2 power, that means where's it showing up? In the bottom under a square root, right? That's kind of cool. So we have in the bottom under the square root a 2 plus x squared plus y squared. And I notice that this 2 cancels with that 2, and so I just have an x in the numerator, right? And actually, I think you can compute pretty quickly that fy is going to be the same thing with a y in the numerator. So I agree, this one's not too bad. Whereas, yeah, maybe page 1 what I'll do is just find out, okay, can you compute a partial derivative? But when it comes to something like this, those will be pretty easy, hopefully. All right, but it also says evaluate it, so let's do that. Although you know how to do that, right? Yes. What do you get? Well, we're probably going to need it, so I'll do it. So we have the square root of 3 over, and then isn't that square root of 6? Comma, and then this one is 1 over the square root of 6. By the way, the square root of 3 over the square root of 6 is the same as 1 over the square root of 2. So maybe that's a nicer way to write it. So far, so good? Part B. They asked me to find all angles theta with respect to the positive x-axis associated with directions of maximum increase, maximum decrease, and zero change, right? So we know that the gradient gives you maximum increase, maximum decrease, right? So in particular, like, let me plot the gradient vector, guys. I think that's actually worth doing. I'll plot it in pink. Look at that. So what are we doing? We got to go, which is bigger, 1 over square root of 2 or 1 over square root of 6? Well, square root of 6 is bigger than square root of 2. So 1 over square root of 2 is bigger. If I remember that, that's like 0.7, right? So it moves more in the x direction than it does in the y direction. So it seems to me that it's moving in this direction, right? That's the gradient vector, something like that, along the plane. And what that says is, if I move in that direction, that's how I get maximum increase on the surface p hat. Does that make sense to you guys? So now what the problem is asking is, what angle does that pink vector make with the x-axis? Like if you moved it, right? It would make some angle. I'll call that angle there theta. What is that angle? Okay. And there's a formula that we should know, right, about the angle between vectors that really kind of gets it for me, right? Because what's the vector right along the x-axis? That's the vector I, it's called, right? 1, 0. And so what you're really doing here, okay, is you're trying to find theta. And the formula I want is that the cosine of theta is, let's say, gradient of f evaluated at square root of 3, 1, dot I over magnitude of the gradient of f, and then magnitude of I. But this can really be simplified, right? Because what do you guys know about I? I is a unit vector, right? And this I here, when we dot it, we're just going to get that 1 over square root of 2. So I get that the cosine of theta is equal to 1 over the square root of 2 over the magnitude of this vector. So we need the magnitude of 1 over the square root of 2, 1 over the square root of 6.
Well, can we just,
Sure.
Can you just do like inverse tangent of the gradient?
Inverse tangent of the gradient.
Like inverse tangent of 1 over radical 6 over 1 over radical 2?
So you want to use the fact that tangent theta is, in this case, right, 1 over square root of 6 divided by 1 over square root of 2. Can I see that?
Thank you, because that's what I did. I was afraid that.
Oh, yeah. You can see it from the picture.
Yeah.
You can see it from the picture.
1 over square root of
Much
2
better.
is a lot easier.
Much better. I like that better, Matthew. Thank you. So, I mean, you could see it, right? Because it's y over x. If we broke this pink vector into its y and x component, then we have that. I do like using tangent better. That's better. You're right.
Can you use that if it wanted us to find it with a different coordinate?
Yeah. You can use this lots and lots and lots of times. And that's one of my reasons for bringing it up. I guess what we should do is finish the problem. So 1 over square root of 6, 1 over square root of 2, so I'm getting square root of 2 over square root of 6, right? So I'm getting 1 over the square root of 3. Yeah? That's kind of nice. If I continued to do it the way I was doing it, the magnitude would be the square root of a half plus a sixth. What's a half plus a sixth? That's 4/6. Take the square root of 3. Oh, you get square root of 1 over 2 over square root of 3. So you get square, hold on. 1 over the square root of 4/6 would be the square root of, that's giving me square root of 3 over 2. So,
1 half become 1.
Yeah, where's the one?
Numerator.
1 over 2.
oh yeah, thank you. So we have 1 over square root of 2 divided by 2 over square root of 3. So it's basically what you get is you get that the cosine of theta has to equal the square root of 3 over 2. And that's the same as the tangent of theta being 1 over the square root of 3. In either case, do you guys get that theta is 30 degrees or pi over 6? Is that what we got? Let's check.
That's right.
Yep. Okay.
So that's the maximum increase, but they also asked to find the maximum decrease and the angle for no change.
Right. So maximum decrease, opposite way. So add 180 degrees to this, right? Or maybe subtract 180 degrees. Maybe you say negative 150, right? So maximum decrease is definitely the other way. What about no change? What about no change? Well, we want to be we want to be the median between, right? Here's maximum decrease. I drew it in gray. No change is where you're actually moving along a level curve, right? By the way, the level curve of this thing looks something like that. So to move along a level curve, we want to be normal to these two. And actually, let me go back to this, okay? You know, let me write it this way. The slope of the line that is pink and gray, I should actually use the colors, huh? The slope of the line that is pink for maximum increase and gray for maximum decrease is, well, we worked it out, right? This is what you did, y over x, so it's 1 over the square root of 3, right? That's the slope of the line. Do you guys know how to find? So the slope of the line orthogonal to this one, what's the trick? It must be negative, right? Do you know what? Radical 3 over 1. It's the negative reciprocal. Basically, in the plane, perpendicular lines, their slopes always multiply to equal negative 1. So I guess this would be the other answer, right? Here's your two answers. Well, okay, I'm not there yet, right? They want the angle, but you could do this, right? You could say tangent of theta is negative square root of 3, and you could inverse tangent that. What'd you get?
Negative 60.
Negative 60. Negative pi over 3 or negative 60 degrees. Okay, because we'd probably want degrees for this kind of a situation. How we doing so far, guys? Okay? Okay. Part C. Write the directional derivative as a function of theta and call this function g of theta. Okay. So yeah, so how do we do this? Well, we'll move on to the back. Part C, same problem. The directional derivative is always given in terms of a unit vector, right? But here, maybe the thing to do here is to say my unit vector that I want is going to be cosine of theta, sine of theta, right? And so I had a formula for you guys. I said the directional vector of f with respect to u, remember the formula? Take grad f, right? You have to evaluate this. So this should see. I should say at the point, let's say AB. Grad f evaluated at AB, and then do what? Dot it with, well, with whatever this is, right? This u. So this is kind of the formula I'm going to use to do this. But my u is going to be cosine theta, sine theta, and then I'll have, you could pick any vector you want coming out of P, and you could get the directional derivative then. Okay, that's kind of the idea. So let's see how this all works. Did we compute grad f yet? Yeah, we did, right? Didn't we do that in part A?
Yep.
That was this one. This one. At that point, it's 1 over square root of 2, 1 over square root of 6. So I'm going to take 1 over square root of 2, comma, 1 over square root of 6, and I'm going to dot it with u, and so I get 1 over square root of 2 cosine theta plus 1 over square root of 6 sine theta, okay? And this will give me the value of the directional derivative. Okay? Part D. Find the value of theta that maximizes g of theta. Oh, we're supposed to call this g of theta. So call this thing g of theta. Right? Well, how do you maximize g of theta? That's a Calc 1 problem. I mean, you know the answer because we already did it, right? We did the gradient. But I think if I were in Calc 1, I could take g of theta. Let me compute g prime of theta. That's kind of the idea here. Negative 1/2 sine of, negative 1 over square root of 2 sine of theta. And then wouldn't it be plus 1 over square root of 6 cosine theta? Yeah? And why did I take the derivative? We can set it equal to 0 and find critical values. Well, in theory, do you guys know how to solve that? Good. 1 over square root of 2 sine theta is equal to 1 over square root of 6 cosine theta. And so what I'm going to do is say sine theta over cosine theta is tangent theta equals, and then I'll bring so I divided both sides by cosine to make that, and then I multiply both sides by, hey, I think I just saw this equation, right? 1 over the square root of 3. Yep. Same answer. That's kind of nice. It shows you that our gradient equation worked. Back when Matthew said, hey, shortcut, Paul, tangent theta. Well, he's right, but here's why. But thank you for that. E. Verify that the value of theta that maximizes. Yeah, we did that. Verify that it equals the. Verify that the maximum value of g equals the magnitude of the gradient. Okay. So they want you to plug in. Yeah. Have fun. That's easy. Okay.